Hello. In the videos on classical probability and non-classical probability, we have learnt about the humble Bernoulli random variable. In this video, and on the one on the geometric random variable, we will learn how we can construct new, more complex random variables by generating multiple independent Bernoulli random variables. In particular, by the end of this video, you should be able to explain what types of phenomenon can be modelled using a binomial random variable, and explain the derivations for the binomial random variable. Before we get onto that, however, let's first briefly review what we have learned thus far about probability. One of the most important things we have learned is the definition of the cumulative probability distribution function. We have learnt that we define the cumulative probability distribution function by requiring that if each event S in the sample space omega has a value x of S taken from the set of real numbers script R, then there exists a cumulative probability distribution function, capital F underscore x of small x, that maps each subset of omega that can be formed using A of x equals this piece of set builder notation to a number from the set of real numbers between 0 and 1. We've said that this function has the following three properties. As you go to its limit as you go to minus infinity is 0, its limit as you go to plus infinity is 1, and it has the property of right continuity. When we've introduced this definition, we saw how it would work by considering a Bernoulli random variable, which we treated as a coin toss. If we go through this example once more, we've seen that the sample space of outcomes for this particular experiment contains two possible events. Either the coin comes up tails, or the coin comes up heads. We have then done this business of giving each event in the sample space a value of x of s taken from the set of real numbers, by saying that tails is given the value 0, while heads is given the value 1. With this mapping in place, we are then able to construct the cumulative probability distribution function with relative ease. We know that the set of elements that have x of s less than 0 is the empty set. As there are 0 events in this set, the cumulative probability distribution function is 0 for all values of x less than 0. We then know that the set of elements that have x of s less than or equal to 0 contains tails only. The cumulative probability distribution function thus changes discontinuously at 0 and, because the coin is fair, now takes a value of 0.5. For values greater than 0 and less than 1, the cumulative probability distribution function is equal to 0.5, as there are no new outcomes in the sample space omega that have x of s values between 0 and 1. This changes when x equals 1, however, as now both heads and tails have x of s less than or equal to 1. Consequently, the cumulative probability distribution function jumps to 1 at x equals 1. Furthermore, the function remains at 1 for all other values of x. The cumulative probability distribution function is illustrated in the figure shown on this slide. The purpose of this video is to now consider what happens when we generate multiple Bernoulli random variables like this one. A useful way to illustrate this process of generating multiple Bernoulli random variables is to consider a tree diagram. The simplest tree diagram, the tree diagram for the tossing of a coin, is shown on the slide here. There are two branches to the tree, one corresponding to the event of getting tails, and one corresponding to the event of getting heads. One way of thinking about this diagram is to think about it as a representation of what might happen in the future. In this particular example, I know that I am about to toss a coin. I am thus guaranteed to end up in one of the two possible futures shown here, the future in which I get heads and the future in which I get tails. I can thus think of these two possible futures as branches in my tree. Let's now be more qualitative and ascribe probabilities to these two possible outcomes. Notice that I have at no point stated that the coin is fair. I should therefore not ascribe a probability of 0.45 to the outcome of getting heads, as the coin may be biased. I will thus state that the probability of getting heads is equal to p, and that the probability of getting tails is equal to 1 minus p, as I must get either heads or tails in my experiments because there are no other outcomes. I now suppose that once I have tossed the coin once, I will toss it again. Our two possible futures, the futures where I get heads and tails in the coin toss, thus bifurcate again. And I now find that I have four possible futures: a future in which I get heads followed by a second heads, a future in which I get heads followed by tails, a future in which I get tails followed by heads, and a future in which I got tails followed by a second tails. Furthermore, because I have implicitly assumed that tossing the coin once has made no difference to it, I can assume that the probability mass function for the first and second Bernoulli random variables that I have generated are identical. The probabilities of the various branches in my tree diagram are thus shown here. As an aside, it is interesting to note at this stage that many statistic books and statistics questions go to great pains to state that they are considering coins that are fair and not biased, despite the fact that biased coins are largely a figment of the mathematician's imagination. Seemingly less effort is expended on explaining that coin tosses are independent and identical. This is an equally important assumption, however, but one that is more often assumed without comment. We now return to the question of the binomial random variable, and to what experiments we are going to model using this random variable in particular. The binomial random variable would be used in this case to model the probabilities of getting 0, 1, and 2 heads from these two identical and independent distributions, or Bernoulli random variables. We can calculate these probabilities easily from our tree diagram by taking advantage of what we have learnt elsewhere about the probability for a pair of random events. In particular, we know that if two events A and B are independent, the probability of observing both of them is just the product of the probability of observing A multiplied by the probability of observing B. In this case, the probability of getting 2 heads is just the probability of getting heads in the first experiment multiplied by the probability of getting heads in the second experiment. The probability of 2 heads is thus simply p squared. The probability of getting 0 heads is similarly straightforward. We multiply the probability of getting tails, or as it is otherwise known, not heads, in the first experiment by the probability of getting tails in the second experiment, and find that this probability is 1 minus p all squared. The probability of getting 1 head is slightly more difficult, as there are two outcomes that give this result, namely heads in the first experiment and tails in the second, and tails in the first experiment and heads in the second. To calculate the probability for each of these two outcomes separately, however, we can take the advantage of the fact that the outcome from each individual coin toss is independent once more. We can then further note that one cannot simultaneously observe heads followed by tails and tails head followed by heads. In other words, these two distinct outcomes are mutually exclusive. Remembering that if events C and D are mutually exclusive, we can calculate the probability of observing C or D by taking the individual probability for observing C and adding to this the individual probability for observing D. We can thus state that the total probability of observing 1 head is thus just 2 multiplied by p times 1 minus p. By repeating this business with tree diagrams, we can arrive at the following formula for the probability mass function for the binomial random variable. This function gives the probability of getting exactly k successes, or in other words, exactly k identical outcomes, from a set of n independent and identical Bernoulli trials. This is an enormously useful random variable, which you will find used in many parts of statistics and in many applications of the subject. Before we leave this business of the binomial random variable behind us, let's take a moment to dwell briefly on the binomial coefficient that appears in this equation, so as to understand where this quantity comes from. It turns out that we need the binomial coefficient because there are multiple ways of arranging the k successes amongst the n trials, as we have already seen in our two-coin example. In that two-coin example, I showed that there were two ways of ordering the successes and failures if we wanted the probability of having exactly one success. The success could have come on the first trial, or the success could have come on the second trial. The binomial coefficient thus comes from considering the mathematics of counting the number of arrangements or things, as it is otherwise known, the field of combinatorics. In these last few slides, I will thus explain the aspects of combinatorics that we need to understand in order to grasp why the binomial coefficient appears in the binomial random variable. In other words, I will explain why the binomial coefficient allows us to calculate the number of ways of arranging the k successes amongst the n minus k failures. Before considering this business, however, let's consider a simpler question. How many ways are there of arranging n distinguishable objects? In other words, how many different looking ways can we arrange n objects if we can tell apart all the individual objects? To explain this, I will consider coloured circles like the blue one shown here. If I have only one circle, there is only one arrangement. The moment I introduce a second red circle, however, I find that there are now two arrangements, namely red-blue and blue-red. Furthermore, on introducing a third green circle, I find that there are three places that I can place the green circle in the blue-red pattern shown here. That is to say, I can introduce the green circle before the blue and red circles, after the blue and red circles, and between the blue and red circles. Furthermore, if I remember that there are two ways of arranging the red and blue circles, I find that there are 6 arrangements of the 3 balls in total, namely red-green-blue, red-blue-green, blue-red-green, blue-green-red, green-red-blue, green-blue-red. There is a simple pattern to observe here. In general, if we have n distinguishable objects, there are n factorial ways of arranging them. To convince yourself of this, pause the video and enumerate all the ways of arranging 4 distinguishable objects. We are now in a position to answer our original question on how to arrange the k successes and the n minus k failures amongst our n Bernoulli trials that we have performed in generating our binomial random variable. To do this, we need to suppose that we have only 2 types of objects, successes and failure, or, in the pictorial example shown here, red and blue circles. Normally, we cannot distinguish between any pair of red circles or any pair of blue circles. Let's suppose for a moment that we made all these objects distinguishable by giving them all numerical labels as shown here. We now know from the rule that we have just learned that there are 6 factorial ways of arranging these objects. The problem, however, is that in actuality we cannot distinguish between the red circles. If we swap these 2 red circles, the sequence appears to not have changed. Help is at hand, however, as we can use the rule we have just learned to calculate the number of identical ways there are of arranging the 4 red circles in this sequence, and the 2 blue circles. In particular, there are 2 factorial ways of arranging the 2 blue circles in any given sequence, and 4 factorial ways of arranging the 4 red circles in any given sequence. In other words, there are 2 factorial times 4 factorial ways of arranging the individual blue and red circles in every distinguishable arrangement of blue and red circles. The number of distinguishable arrangements of blue and red circles can thus be found by taking the 6 factorial ways there would be of arranging the circles if they were all distinguishable, and dividing this by 2 factorial multiplied by 4 factorial to reflect the fact that each distinct arrangement of circles can be constructed in this number of ways. This is how the binomial coefficient is defined, and it is how we can calculate the number of ways of arranging the k successes and the n minus k failures in our binomial random variable. We thus conclude by summarizing the content of this video. We have introduced the binomial random variable as a way of modeling the performing of n independent and identical Bernoulli trials. We have introduced the probability mass function for this random variable and explained how the elements of this probability vectors give us the probability of 0, 1, 2, and so on successes amongst our n trials. Furthermore, we have seen why the binomial coefficient can be calculated using the expression shown at the top of the slide, and why this quantity is instrumental for the calculation of the elements of the probability mass function for this random variable. Make sure you can answer all the questions below before moving on, and then try the programming exercises in the associated Python notebook. Thank you for your attention.